Hi, my name is Daniel Ormelum, and this is the completed SAR ADC build originally created by Mitsuru Yamada. This analog to digital converter takes an analog input, in this case a potentiometer, and converts it to a digital binary representation, these LEDs. Unfortunately, due to leakage in my sample and hold IC, it does not properly display the binary representation of an analog input as seen when I turn the potentiometer, but on screen there is a video of when it works to an extent. Looking at the schematic of the 7-bit SAR ADC, there are a few main parts I split the circuit into. The clock and successive approximation, consisting of the inverter-based clock from the first stage of SAR ADC, and a 74HC273 octal D flip-flop, which I'll refer to as IC1. The data comparison, consisting of D flip-flops, the R2R DAC, the AND gates, and the comparator, and finally the output, consisting of the second octal D flip-flop, which I'll refer to as IC2, the LEDs, and the slide switch. The output of the inverter-based clock, running at 10 kHz as proposed by Yamada, which was confirmed in the first part of the SAR ADC, clocks IC1. Each output of IC1 connects to its next input, seen through these nets. This allows for the successive approximation of each bit, as on the first clock tick, the high on D0 shifts to Q0, which is connected to D1. On the second tick, the high on D1 shifts to Q1, which is connected to D2, and so on. The data input of each D flip-flop on the 74HC74 dual D flip-flops, which are ICs 2 to 5, all come from the output of the comparator. This input is shifted on each clock tick when the respective output from IC1 goes high. Additionally, each flip-flop is preset to 1 as the output of Q7 from IC1 goes high after the previous approximation cycle, so on the 8th clock tick. This inverted output clears IC1 and presets the flip-flops. Each output of the flip-flops connects to the inputs of the AND gates. Other than the first AND gate, whose input is permanently tied to 5 volts, each AND gate outputs a low initially, as each output from IC1 starts low. This leaves the MSB as the first approximation, shifting down after each clock tick to perform the analog to digital conversion. For example, let's say we have an analog input voltage of 4.2 volts. Before the first clock tick, the AND gate providing the MSB for the DAC is high, as one input is permanently 5 volts and the other is high from the preset flip-flop. At this point, every output from IC1 is 0, meaning every other AND gate is outputting a 0. This results in the DAC output being Vref over 2, or 2.5 volts. On the first tick, Q0 of IC1 goes high, which puts a high on D1 and also clocks the first flip-flop, shifting the result of the comparison between 4.2 volts and 2.5 volts onto its output. Since 4.2 volts is greater than 2.5 volts, Q0 will remain as 1 until the next approximation cycle. Now that IC1's first output is high, the second AND gate's output goes high, providing Vref over 2 plus Vref over 4 as the output of the DAC, or 3.75 volts. On the second clock tick, Q1 of IC1 goes high, D2 gets a high, the second flip-flop gets clocked, and the 1 from the comparison of 4.2 volts and 3.75 volts gets shifted to Q1. This keeps on happening until you get the final analog to digital conversion binary representation. In Yamada's SAR ADC, there's also a manual mode. The only difference is that a button press is needed to clear IC1 and preset the D flip-flops on ICs 2 to 5 instead of automatically resetting after the 8th clock tick. This means that each button press starts a new conversion cycle, resulting in your new output 8 clock ticks later, which appears instantaneous since the clock runs at 10 kHz. My name is Daniel Ormelum, and thank you for listening.